Okay, so let's start. Maybe other people will join soon. So this is a. So we usually have a traditional summer school in the last week of August in Novosibirsk to bring people from Siberia to topics we're interested in. But of course now it's impossible to make it. So we're making it online. So making the conference, small conference online together with Miami and with Bulgaria. So we have more organizers and more people can join, of course, because it's online. So let us start from the first short course of 2 lectures given by Tony Yue from Paris, and the title you can see, it's Frobenius structure, conjecture, and moduli of Calabi Yau pairs. Tony, please.
Sure. Thank you very much for the introduction, and thank you for inviting me to this summer school. The title of my talk is Frobenius structure, conjecture, and the moduli of Calabi Yau pairs. So the plan of my talk is follows. First, I'll talk about the Frobenius structure conjecture. And the second, I will try to construct structure constants of the mirror algebra. And then I will explain an application to the moduli space of Calabi Yau pairs. After that, I will explain a generalization of the Gelfand-Kapranov-Zelevinsky secondary fan. And finally, I will explain how to glue mirror families over the secondary fan. So let's start with the Frobenius structure conjecture. The motivation comes from mirror symmetry. Mirror symmetry is a conjectural duality between Calabi Yau manifolds. Roughly, mirror symmetry says that for any Calabi Yau variety X, there exists a mirror Calabi Yau variety X check such that there are plenty of geometric relations between the two varieties. So let me mention that if you have any questions, you can just interrupt. You can just unmute yourself and interrupt me. There are not so many participants, so feel free to do so. The philosophy of mirror symmetry is that one may build the mirror X check by counting curves in X. And the Frobenius structure conjecture of Gross-Hacking-Keel is a precise yet simple formulation of this philosophy for log Calabi Yau varieties, which boils down to intricate relations of counts of rational curves. And the question is, what are the curves that we count? So now let me explain the idea of Gross-Hacking-Keel. Here is their setup. So we fix K any field of characteristic 0. For example, we can take the field of complex numbers, but our theory is essentially algebraic. We also fix U an affine smooth log Calabi Yau variety over K. By log Calabi Yau, we mean that all log pluricanonical bundles are trivialized by the tensor power of by some tensor power of a volume form. And we consider Ku the field of rational functions on U. And then we consider a set SKUZ. It's called the set of integer points in the essential skeleton of U, but it's okay if you don't know yet what it means, because we have an explicit description of this set. It's just the disjoint union. It's just a 0 disjoint union M nu, where M is a positive integer and nu is a divisorial valuation on the field of rational functions on U where omega has a pole. So divisorial valuation one can always get by taking some compactification of U, and it's given by some component of the divisor at infinity, and we consider multiples of such divisors where omega has a pole. And furthermore, we fix a projective normal crossing compactification Y of U with complement denoted by D. So we have U, some log Calabi Yau variety, some compactification Y, and the complement we denote by D. So now let me explain what are the curves that we count for the Frobenius structure conjecture. So we are given an n-tuple of points in this SKUZ. So the name is integer points in the essential skeleton. It has a more intrinsic definition, but we can just use this explicit description. So we fix an n-tuple of points in here, and also some curve class in the cone of curves. So we write the cone of curves just because it's essentially an algebraic theory. You can also work just with homology class, for example. And now, by our explicit description, we write Pj as Mj nu j for all non-zero Pj, and assume each nu j is given by some component dj of d, which is always possible by some blow-up. Then we define eta p beta to be the number of closed rational curves in Y of class beta that intersect dj with order mj for every non-zero pj. And here is the picture of the rational curves that we count. So this is the counting numbers that we use in the Frobenius structure conjecture. And if you are not happy with this quick heuristic definition of counts, here is the precise formulation. I mean, we can always say we define the number to, we define this to be the number of something, but we should prove something that, for example, it's a finite number and it's well defined and so on. So here is the precise formulation. Let Hp beta be the space of maps from P1 with n+1 marked points to Y, such that for every non-zero Pj, F sends this marked point Pj to the this open strata, interior part of the divisor dj with order mj. So we have P1, P2, P3. And the first condition is that each Pi maps to Di with given order M, or each Pj maps to Dj with given order Mj. And
may I ask you a question? So sure. You choose this point, P1, P2, and so on. And then is it true that then you choose the boundary divisor Di's? I mean, maybe this point, when you say it's possible, always you can always do some blow-ups. Can it happen that you have valuation at some point, and you if you choose this P1, Pn, then you should blow up Di's, or this divisor is fixed in the very beginning, so, this boundary divisor D.
Yeah, so here when we fix this bold P, this tuple, n tuple, then we make some blow up so that each Pi is given by some component of D. And then this blow up is fixed. There's no need.
So this divisor depends on a point you count in some sense, yeah?
The divisor depends only on this data, this P, the points in this set SKUZ.
Thank you.
And this moduli space, for this moduli space, the divisor, everything is already fixed.
Thanks.
Thank you for the question. I want to send the PDF to the chat. Usually I can do that, but here it doesn't let me do this. Because I think it's easier for understanding if people can also look at the PDF, but I don't know why. I cannot do this here. Can I send a file? Yeah, I will try it next time. So the first condition is the marked points maps to the divisor di with a given order. And the second condition is that the fundamental class of this red curve maps to the curve class beta we fix. And then using deformation theory of curves, one can prove the following lemma. If we consider the map phi, taking first domain of this curve, which gives us a point in the moduli space of curves M0 n plus 1. It's just the moduli space of the domain curves. And also, we take evaluation at the marked point S. And this map is finite étale over a Zariski dense open subset of the target. And now we can precisely define the count of rational curves that we are interested in. The count eta p beta is just the degree of the finite étale map above. So this is the definition of the count. The precise definition, and you can just keep in mind this heuristic quick definition. Let me remark that these counts are particularly simple. They are called naive counts in the sense that we make no use of virtual fundamental classes. Thanks to this deformation theory lemma, we get a particular simple way to count these curves. And we see that our count eta p beta depends on the choice of the tuple of points p and also beta. And if we vary these choices, we get infinitely many numbers. So it's natural to ask what are the relations between all these numbers. And for this, let's assemble the numbers into generating series as follows. So first, we want to take into account all curve classes, and the natural thing to do is to consider the monoid ring over all curve classes. So let R be the monoid ring over all curve classes, which is just a direct sum of copies of Z, copies of integers for every curve class beta, and we denote the basis vector by Z to the power beta. And next, we want to take into consideration all possible choice of P, all possible choice of the points in this, all possible choice of these integer points in the skeleton. So we let A be the free R module with bases inside this integer points of skeleton, SKUZ, which is just direct sum of copies of R for every point in SKUZ. And we denote the basis vector by theta p for every point p inside. So it's nothing mysterious here. We just take direct sum of every possibility. And the notation z beta and theta p, they are just notations for the basis vector. And now we define the following Frobenius form. Let this form be the R multilinear map that sends the basis vectors theta p1 until theta pn to the sum over all curve classes beta of the basis vector z to the beta with coefficient eta p1 to pn beta. Eta is just the count we defined. So here, let me say that there's nothing special of the definition of the Frobenius form. We just put together all possible choices of p and beta. And by the affineness of our log Calabi Yau variety, the sum is a finite sum, one can show. So now let me state the main theorem of this talk. And it's proved in my paper with Gelfand-Kapranov-Zelevinsky. The main theorem of this talk is that if we assume that U contains an open split algebraic torus, then the following hold. First, this Frobenius form we defined above is a non-degenerate form. And the second, there exists a unique finitely generated commutative associative R algebra structure on A such that the basis vector theta 0 is the identity. And moreover, the Frobenius form, the value of the Frobenius form on A1 to AN is equal to the trace of the product of A1 to AN. Here, trace means taking coefficient of the basis theta 0. And 3, so we defined A to be some module, and by statement 2, this free R module A has an algebra, has a finitely generated commutative associative R algebra structure. So it makes sense to take its spec, and we can consider the family spec A over spec R. We call, by motivations from mirror symmetry, we call A the mirror algebra associated to our log Calabi Yau variety, and we call spec, we call this family the mirror family. So the statement 3 is that let TD be the split torus with co-character group generated by the irreducible components of D. Then we have a natural equivariant action of this torus on this mirror family. And the last statement is that if we base change to Q of our mirror family, then we obtain a flat family of affine varieties of the same dimension as U. Each fiber is Gorenstein, semi-log canonical, and K-trivial. So Gorenstein and semi-log canonical, they are conditions on the singularity. Somehow they say that they have a reasonable singularities. And moreover, we show that the generic fiber is log canonical and log Calabi Yau. So this is, it's a bit surprising. It's also predicted by the philosophy of mirror symmetry that when we start with our log Calabi Yau variety and we count rational curves, by counting rational curves, here we obtain another family of log Calabi Yau varieties with some with certain singularities. So let me make some remark of this theorem. First, so essentially the mirror algebra or this mirror family depends only on the log Calabi Yau variety because we are interested in the mirror of the log Calabi Yau. But in the formulation, we have some compactification y, and we can remove the dependence of our mirror algebra on the compactification y of u by setting all curve classes to 0, which means we can take AU to be a tensor with z over r, where the map r to z sends every basis vector z beta to 1. So somehow the mirror algebra is really about u, and the compactification y it's only responsible for making sense of curve classes. And if we ignore curve classes, we get a mirror algebra that is just no longer depends on the compactification. And another remark, the assumption, so we assumed that U contains a torus, and this assumption always holds in dimension 2, but not always in dimension 3. And this plays two roles in our theory. First, it allows a degeneration of the mirror family to a toric variety, which is crucial for the proof of 1 and 4. And second, it greatly simplifies the enumerative part of the theory. If we remove this assumption, we will need a more sophisticated theory, which is still under development. And we conjecture that the theorem may still hold without the torus assumption. And finally, let me mention what is the original conjecture that I talked about in the beginning, the Frobenius structure conjecture of Gross-Hacking-Keel. The original conjecture of Gross-Hacking-Keel is a variant of this theorem, which was stated via log Gromov-Witten invariance instead of naive counts of rational curves, and which does not have the torus assumption. So the reason that it was stated via log Gromov-Witten invariance is because at that time it's not known that we can actually use naive counts of rational curves. This deformation theory lemma about the curves was not known at that time. So they stated the conjecture using log Gromov-Witten invariance, which is a bit technically complicated. But now we can, if we have this deformation theoretic lemma, it's not really necessary here to use log Gromov-Witten invariance for the statement. But actually, it's not clear because log Gromov-Witten invariants are a bit complicated. It's not clear whether these invariants are the same as these simple naive counts. So Gross-Siebert, they are working on the mirror construction problem in greater generality using the theory of punctured log curves. And the comparison between their algebra and the one I explained above, it's not so obvious. So now let me explain the structure constants of the mirror algebra. In the statement of the Frobenius structure theorem, it's claimed that this A, the mirror algebra A, which was first defined as some free R module, has some commutative associative algebra structure. So the question is, how are products defined in the mirror algebra A? Since it's R algebra, and in order to define the products, it's enough to define it over the basis elements. So given some points P1 to Pn in this set SKUZ, some integer points in the essential skeleton, we write the product in the mirror algebra A of theta P1 of the basis elements, theta P1 to theta Pn, as follows. So this product is supposed to be an element in A, and recall that A is an R algebra with basis this set SKUZ. So we can just write this element as sum over all points in SKUZ of the basis vector theta q with some coefficient in R. And next, recall that R is some monoid ring over the cone of curves. So we can write this element as sum over all curve classes of the basis vector z to the gamma with structure with some coefficient. And we denote this coefficient by chi P1 to Pn Q gamma, and they are called structure constants. So now the point of the second part of my talk is to explain how do we get these structure constants. Here is the idea. Inspired by Kontsevich homological mirror symmetry, we would like to define the structure constants chi, these structure constants chi, as counts of holomorphic disks. And note that disks do not make sense in algebraic geometry. So we have to go to analytic geometry. And the first choice is a complex analytic geometry. It doesn't really work because counts of disks in complex geometry or symplectic geometry give rise to complicated so-called curved A-infinity structures. And it's not clear how to get well-defined numbers of counts from these A-infinity structures. And our solution is to use non-Archimedean analytic geometry. If we use non-Archimedean analytic geometry, then we can actually have a very simple and direct definition of the structure constants chi by counting non-Archimedean curves. I will explain in a second. Although studying the properties of such counts requires harder work. To define them, it's pretty direct, and proving the properties is a bit more complicated. So now let me explain how non-Archimedean geometry comes into play. For using non-Archimedean geometry, we equip our base field K with the trivial absolute value, which is a map from K to the two-element set 0, 1, which sends all non-zero element of K to 1 and sends 0 to 0. So this is called a trivial absolute value. And with this trivial absolute value, K becomes a non-Archimedean field. And once we have a non-Archimedean field, we can apply the theory of Berkovits analytification, and we obtain, so U, recall that U is a log Calabi Yau variety over K, and now K is a non-Archimedean field. So by Berkovits analytification, we obtain a K analytic space U1. If you didn't know the theory of analytification over non-Archimedean field, you can just think that it's analogous to complex analytification. So over a complex field, when we have a complex algebraic variety, we can analytify and get a complex analytic space. Here, similarly, when we have an algebraic variety over a non-Archimedean field, we can analytify and get a non-Archimedean analytic space. And let me just quickly recall that the underlying set of the analytification is simple to describe. It consists of pairs Xi nu, where Xi is a scheme theoretic point, and the nu is an absolute value on the residual field kappa Xi, extending the given one on K. So in particular, let me remark that this set SKUZ is a subset of the analytification of U. And as an example, by assumption, U contains a torus. We denote by M the co-character lattice of the torus, and then we have SKUZ is canonically identified with SK of the torus Z, because all these divisorial evaluations, since they don't really see, they really only depends on the field of rational functions. So it's birational invariant. And for the torus case, this set is simple to check, it's simple to compute. It's just the co-character lattice. And recall, our goal is to define the structure constant chi by counting some non-Archimedean analytic disks. So what do we count? Heuristically, we want to define this structure constant chi P1 to Pn Q gamma to be the number of holomorphic disks in the analytification of Y like this. So here are the heuristic conditions that we impose. First, as in the definition of the counts for the Frobenius structure conjecture, first, we ask that the holomorphic disk delta intersects the divisors dj with given order mj. So like here, it intersects d1 and d2 with some given order. And the next, we ask that the boundary of the holomorphic disk maps to the point q in this set of integer points in the essential skeleton, which we remarked that it's just a subset of the analytification. So Q lives naturally in the analytification, and we ask the boundary to map to Q. So in non-Archimedean geometry, the boundary of a disk is actually a single point. Just a remark. And we can, the third heuristic condition that we impose is that the derivative at the boundary of the holomorphic disk is equal to Q. So this, we can make sense of derivative using the theory of so-called skeletal curves. I will not have time to explain in this lecture, but you can just think as a heuristic condition. And finally, we ask that the class of the holomorphic disk in the limiting sense is equal to gamma. So that's the heuristic idea for the number of holomorphic disks that we count in order to define this structure constant. And as I said, that it doesn't always make sense to say that let something be the number of something, because that might be an infinite number. So here we have this trouble. And unlike the situation for counting closed curves above, the space of all such disks is infinite dimensional. There are so many such disks, we cannot really count. The moduli space is actually infinite dimensional. So we ask how can we extract a finite counting number from this infinite dimensional space? The idea is to reduce to finite dimension by imposing a regularity condition on the boundary of our holomorphic disk, which we call toric tail condition. So this is our disk, our holomorphic disk, and we ask that by analytic continuation at the boundary of the disk, our disk extends to a closed rational curve in the analytification of Y. So this blue part is analytic continuation, such that first, if we write Z to be the opposite of Q, and we write Z as mz times nu Z, since any element there can be written as, except 0, can be written as some multiple of some divisorial valuation, and say that this nu Z has divisorial center dz, then we ask that the tail, the blue tail, hits the divisor dz with order mz. And the second, we ask that the punctured tail, meaning that the blue tail minus the marked point z, should lie inside the torus. So this is the extra condition that we impose for counting holomorphic disks. And now, the good news is that once we add this extra toric tail condition, we get finite counts of non-Archimedean disks. Yeah, so this is the heuristic idea for counting such red disks, and the counts of such red disks give the structure constants. And I think I still have time to give a more precise mathematical formulation. You don't have to pay too much attention to the precise mathematical formulation. I just want to go quickly over it in order to show that to make this heuristic idea precise is not so complicated. What is complicated is to prove that the counts has good properties, but it's not so complicated just to define them. So let me just quickly go through the precise mathematical formulation for counting this red curve. In the first step, we have to figure out the class of the added blue tail, T, and one can check that the class of the tail is equal to the class of the closure of any general translation of the one-parameter group in the torus given by Q. And this can be checked by tropical geometry. So we can figure out precisely what's the class of the tail. And the second, we should set up the moduli space for the extended curves. So recall we have Z. Z is the opposite of Q, and we consider a tuple PZ combining all the points Pi with Z. And we define beta to be gamma, the original curve class, plus the curve class of the tail. So beta is the curve class of the total rational curve. Then, as in the definition of counts for the Frobenius form, we consider the moduli space HPZ beta with marked points labeled as P1 to Pn ZS. So recall that this moduli space consists of rational curves in Y of class beta, whose intersection numbers with the boundary D are given by the tuple PZ. And we have a natural map phi, whose first factor takes domain of our curve, and whose second factor takes evaluation at the marked point S. And in next step, so we want to recall that in the definition of the Frobenius form, we took some degree of this map and we get the number. Here we have to be a bit more careful. So we need to specify a particular point in the target. So first we pick a specific modulus in the first factor, M02. We let mu be the divisorial valuation given by the divisor in the Riemann for the compactification, parameterizing nodal curves like this, separating the first n marked points with the last two marked points. And we let Q tilde be the pair mu Q seen as an element of the analytification of the target. Recall that phi is finite a tau over a Zariski open of the target, then the pre-image by phi of this point Q tilde is finite. It's a finite analytic space. And so beware that not all curves in this pre-image are good. Not all of them are extensions of disks by toric tails. They can have something wild there. And we want to discard those wild things because all we are interested in are the counts of these red disks. We don't, and this toric tail is just an auxiliary tool for us to count these red disks, and we don't want any wild stuff happening outside the disk. So we want to discard all those. Then in the last step, we impose the toric tail condition. Definition: a map F from a rational curve with marked points n plus 2 marked points to the analytification of Y is said to satisfy the toric tail condition if the following holds. So a non-Archimedean analytic rational curve as the underlying topological space of a non-Archimedean rational curve, it's an infinite tree. And we have some marked points of the infinite tree. We can take its convex hull, we denote by gamma, which is a finite subtree. And we have a canonical retraction from the infinite tree C to the finite subtree gamma. Then the tail T is the preimage by R of the path connecting S and Z. This is our tail, and the tail condition is simply that we want the punctured tail to lie in the torus. And finally, we let F be the subspace in the preimage satisfying the toric tail condition. So everything, so here, everything is self-contained, and we obtain the precise definition of the structure constant. Chi, P1 to Pn Q gamma, is just the length of this finite analytic space. So finite analytic space is just some points with some nilpotents, same as finite scheme. If you don't like to take length, it's the same as taking the cardinality after passing to some algebraic closure. So this is the precise definition of structure constant. I just want to show you that the self-contained definition is pretty short, but eventually all you need to keep in mind is just the heuristic idea. The count of such holomorphic disks is responsible for the multiplication of the mirror algebra. So now we conclude that the structure constants, so theorem, the structure constants defined as above, they are independent of the choice of torus. And moreover, the sums in the multiplication rule using the structure constants are finite and give the finitely generated commutative associative R algebra structure on the mirror algebra A in the Frobenius structure theorem. And remark, although the precise definition of structure constants is rather self-contained and straightforward, the proof of their properties requires more machineries to be set up, especially deformation invariance and the theory of skeletal curves. So that's all I want to explain for the Frobenius structure theorem or the Frobenius structure conjecture. And now I want to talk about some application. So this theorem has an immediate application to the theory of cluster algebras, which we skip in this lecture, and let us turn directly to an application towards the moduli space of Calabi Yau pairs. I have written something about applications to cluster algebras in my notes, but I have trouble to send it to you in Zoom, so I'll figure out how to send it after the talk. And let's go directly to the application to the moduli space of Calabi Yau pairs. So concerning the moduli space of Calabi Yau pairs, in the preprint by Paul Hacking, Sean Keel, and myself, we make the following conjecture. we conjecture that any connected component Q of the moduli space of triples X, E, which is sum of E1 to En, and theta, where X is a connected smooth projective complex variety, E, living in the anticanonical class of X, is a normal crossing divisor with a zero stratum, where every component EI is smooth, and theta is an ample divisor not containing any zero stratum of E. And we conjecture that all connected component Q of the moduli space of such triples is unirational. So in general, we don't know much about the explicit geometry of the moduli space of such Calabi Yau pairs. We know something such as existence of moduli space, projectivity, like properness, projectivity, separability, and so on. But the explicit geometry, we are quite ignorant. And this unirationality, it's not at all clear from birational geometry. And we also have a more precise form of the conjecture above for the compactified moduli space. Let me recall some basic notions from birational geometry in the end of this lecture, and in the next lecture I will go to more details. So recall, a pair X delta consists of a reduced pure dimensional variety X and an effective Q divisor delta, none of whose irreducible components is contained in the singular locus of X. Then a Kohler-Shepard-Baron-Alexeev KSBA stable pair is a proper semi-log canonical pair X delta such that Kx plus delta is ample. The notion of semi-log canonical is a condition on the singularities which generalizes nodal singularities to higher dimensions. A Calabi Yau pair is a proper semi-log canonical pair X delta such that Kx plus delta is Q rationally equivalent to 0. And a polarized Calabi Yau pair is a triple Xe theta, where Xe is a Calabi Yau pair and theta is an ample divisor not containing any SLC center of the pair Xe. In other words, the pair X, E plus some small multiple of theta is a stable pair for sufficiently small epsilon. And thus, we see that for sufficiently small epsilon, taking this pair X, E plus epsilon theta, our moduli space Q of triples Xe theta immerses into SP, the moduli space of stable pairs, which is a generalization of the Riemann for the compactification MGN bar of stable curves. And now we can state the precise form of our conjecture, which says that if we consider the closure of our moduli space Q in this moduli space of stable pairs SP, then it admits a finite cover by a complete toric variety T. And let me stop here for today. In the lecture tomorrow, I will explain how mirror symmetry and the mirror family that we constructed in the proof of the Frobenius structure conjecture can be applied to study, to prove a special case of this conjecture and for the study of the moduli space of Calabi Yau pairs. So yeah, I'll stop here for today, and thank you very much for your attention.